Today, we're going to talk about epoxides, and then we're going to spend some time on multi-step synthesis. Because on your unit test, you'll recall that on the Unit 1 test, I had you guys do mechanisms from OChem 1 and some structural drawings just to show me that you can do bond line structures. On the Unit 2 test, I had you do a multi-step synthesis and a mechanism, but on the Unit 3 test, it's it's one multi-step synthesis and one roadmap. And my roadmaps are things like, I give you A, and I give you number 1, and then you need to fill in some of the other components. You need to fill in the first and the last reagent, and you need to fill in the intermediates. And so you get some information. It's kind of like a guided multi-step synthesis. And what I like about these is that even if you're not sure what the first intermediate should be or the first reagent, you might be able to figure out those last few things because you've got information along the way to help you fill it in. So you will have a roadmap and you'll have a multi-step synthesis on your Unit 3, Part B. So today I want to make sure that we have time to go over roadmap stuff and multi-step synthesis stuff. All right, so let's talk about epoxides. We did start this yesterday, preparation of epoxides. Previously, we had learned that we can take an alkene, treat it with a peroxy acid, and the one that we used most often was MCPBA. We classified this in the alkene addition category, but if we're being honest, it's not really an alkene addition. Well, it does consume the pi bond, but it actually preserves the same degrees of unsaturation. So it's a unique alkene addition. What we're going to look at now is an epoxidation method from halohydrin. So we can call this the halohydrin elimination epoxidation. Now this one does rely on specific stereochemistry. It requires that our alcohol and our vicinal halide are adjacent to each other. It would be good to use a strong base here, as strong of a base as you can. Although on active, it's very possible that you would see all sorts of bases being used for this. There's no intermediate isolated. This OH group gets deprotonated and substitutes the bromine to create the epoxide. But I want to show you what the intermediate does look like. And I fear it's been a while since I've given you guys acid-base mechanisms. And like I said, you're not going to be tested on mechanisms on this test, this unit test this weekend. But I do want you to have some familiarity with it. Where's my sodium? Huh? Spectator, yeah. So I'm ignoring it. You don't have to ignore it, but what would be the right way to show sodium if I wanted to show it here? Just a little ion off to the side. So could I do this? Why not? No covalent bond. That covalent bond is a misrepresentation of the compound. All right, hydride, very strong base, bonds with hydrogen, gives the OH electrons back to oxygen. This creates a strong nucleophile. And much like any alkoxide, that nucleophile can substitute a halogen. I know, I felt the same way. Okay, now you want to see something really cool. Let's draw this in its chair conformation. In order to have the bromine be a leaving group, it has to be in an axial position. It's a down bromine, so I'm going to show this bromine in a down axial. On the adjacent carbon, my oxygen is up, which is up equatorial. I'm sorry, up axial. And so this oxygen is essentially twisting over and falling in to form that epoxide. I know, those of you that had me for OChem 1, I don't even have you guys draw chairs anymore. So this whole process might be kind of a challenge if you're not sure how to sketch out that chair. But it's an interesting process. Okay. Now, if we were to show that in a bit of a longer synthesis, we know how to make that halohydrin. So we could show an epoxide synthesis by saying H2O and bromine followed by NaH leaves me with an epoxide product. Don't worry about drawing the chair conformation. That was just for fun. How many stable intermediates during this multi-step process? And by stable intermediates, I mean a compound that you could isolate and work up, not a reactive intermediate which forms and then proceeds through more bond breaking and bond forming. Any idea? One stable intermediate. Right. First, the intermediate we get is the halonium ring intermediate. That's reactive to the water. Then we get a protonated halohydrin addition product. That's reactive to whatever basic conjugate base I have. Then I could isolate my stable halohydrin addition product before I run my elimination, and I get a reactive alkoxide intermediate. So there's a lot of intermediates. We're looking at that stable intermediate. This is the only stable intermediate that forms. But this is really the final product that we're interested in. I bring that up because when I was grading your Unit 2 homework and you had multi-step synthesis, sorry, rebooting. When I was grading your multi-step synthesis, I noticed a lot of you in EAS and NAS multi-step syntheses were showing me the mechanisms, showing me the intermediates that form during the mechanisms and how those intermediates attack and react with one another. I just want to clarify, you don't have to show that in a multi-step synthesis. In fact, if this is what you wanted to show, that would work just fine, because we're saying that this now counts as one way of synthesizing an epoxide. You could show it longer and show the alkene forming the halohydrin product, and then a second step to show the epoxide. But all of these other intermediates don't need to be shown unless you're showing a mechanism. These reactive intermediates don't really belong in a multi-step synthesis. I don't care if you draw them out, but it does slow you down. So if you're doing this in a timed setting, having to work through the mechanism every time just to solve a synthesis kills a lot of time. So I want you to be thinking about knowing how your reagents change functional group without having to show the intermediates that form in between. Okay. Those are the ways that we'll form epoxides. Now let's talk a little bit about reactions with epoxide. We call these ring openings. Any idea why? The epoxide's a ring. And if we react with that ring, it's a very strained ring. It has very tight bond angles, high energy. So it's not hard to break one of those bonds and stop having a ring. We can do this in two conditions. We can have acidic conditions, or we can have basic nucleophilic conditions. Does anybody need that same worksheet? We're still working on that same worksheet from last week. But here we actually have an example of an epoxide. Does anybody need this? Okay, we're going to look at this example epoxide and how the two different conditions change the products that we get. Here's, I think I need to spread this out. Here's my epoxide. And we're going to show what happens on the way to a ring opening product in basic or nucleophilic conditions. So what I'm going to add here is just a generic nucleophile, and then I want to give you guys examples of other common nucleophiles that we use. So here's my nucleophile, nuc minus, and I'm going to call it nuc minus because we're in basic conditions. So this is something with a negative charge that could accept a proton, but is also a good nucleophile. When this nucleophile is drawn to the ring, it wants to attack whatever carbon gives it the least resistance. So it goes for the carbon with the least amount of steric strain. Ivana, you're looking for a sheet. Do you want a copy?
Yes, please.
Which carbon has the least amount of steric strain? I know.
What is this?
I'm sorry. We could maybe twist these if you guys want to.
This is my fault.
Which carbon has the least steric strain? Oh, this one here? I agree. That does have the least steric strain, but it's not in the epoxide. Of the epoxide carbons, this has less steric strain than this. Can we agree that this is a primary carbon on the epoxide and this is a secondary carbon on the epoxide?
It only has one other attachment.
Exactly. One other carbon attachment, 2 carbon attachments. So when my nucleophile attacks, it will attack at the least substituted position. Sorry, these are going to be dotted lines. What I have in brackets is a transition state, representing bonds forming and bonds breaking. Nothing's happened, technically. Is my pen going to tip forward or backwards? There's no way of knowing. It's a transition state. Things are changing. It's both forward and backwards until it falls past that energetic transition state. And once it does, then my nucleophile is bonded to my least substituted carbon, and I get an alkoxide on my more substituted carbon. I've opened my nucleophilic ring. Specifically, I've opened it on the least substituted side. Now, I have found that different students prefer to think of this different ways. So I look at this, and I recognize that in basic conditions, my nucleophile adds to the least substituted position. But a lot of times, we're going to take this alkoxide, we're going to run a second step to protonate it, an aqueous workup. First, basic nucleophile. Second, aqueous workup. And that means that we get an alcohol. So some students like to say, in basic conditions, I should get a more substituted alcohol. Do you guys see the difference in that perspective? I like to say, my nucleophile adds least substituted, but some people like to say, my alcohol forms most substituted. It's up to you how you want to think of it. You can think of it kind of like Markovnikov, where Markovnikov says, pay attention to where H adds, but I say, pay attention to where the carbocation adds. Yeah. All right. If I don't want to run it in basic conditions, I'll run it in acidic conditions. But in acidic conditions, my epoxide will protonate. Do you notice what's changed about the epoxide? It has been protonated. There's a hydrogen on it now. And there's a positive charge. It's leaning. Do you see that lean? What is going on with my pages? Why is it leaning? Why is it that one of those bonds has been stretched? Which bond has stretched? Indigo? The positive charge is causing this structure to shift. God, I don't know what I did with all these sheets. And I guess I haven't done a great job of showing it here, because on the version I gave you, the oxygen to the least substituted carbon is a little bit more straight up and down. This bond to the more substituted carbon is stretched further than this bond to the least substituted carbon, which is helping to delocalize that positive charge. It means that the bond to the more substituted carbon is putting a greater and greater partial positive on the carbon. If this bond is elongating, then oxygen is taking those electrons more often and leaving a better partial positive. Why? Why this carbon that gets a better partial positive? Why doesn't it steal electrons from the other carbon? A carbon that's more substituted is always more stable with that positive charge. So this carbon here gives up its bond a little bit more, and it takes on more of that partial positive. This is going to help it be attacked. So when we now introduce a nucleophile, I'm going to introduce this nucleophile as just nuke. We don't necessarily have to show it as nuke minus. Sometimes this is neutral. Sometimes it is still an anion. That transition state that we get this time shows the nucleophile opening the ring on the more substituted side. Because that's where the greater partial positive is, because that bond has been stretched further. In fact, this is actually the same thing that happens in those bromonium rings. The bromonium ring stretches further from the carbon that is more substituted, making it more likely that the nucleophile will attack at that more substituted side. The bromonium ring always gets opened from the more substituted side. The protonated epoxide will also be opened from the more substituted side. And the product that we get after this, the nucleophile has added to the more substituted position, and the alcohol forms on the least substituted position. Structural isomers. I can control the regiochemistry of my ring opening by controlling acidic or basic conditions. How nice is that? So nice. So let's talk about what reagents we'll use in nucleophilic conditions and what reagents we'll use in acidic conditions. I should say that there are reagents that can be used here that I typically don't use. For instance, you can introduce bromine, take an epoxide and react it with HBr, which actually just gives you a halohydrin product. I don't know if that's really useful because we can form the epoxide from the halohydrin, so why are we going backwards to it? But it is possible. In nucleophilic conditions, we'll use things like cyanide, alkoxide, or hydroxide in nucleophilic conditions. Basic. Things that are not protonated. And we can use things like organometallics. I want to give you guys, I want you to be reminded about what organometallics might look like. So methyllithium, phenyl grignard, these are good organometallics, which, by the way, cannot exist in acidic conditions. So they can only be used in nucleophilic conditions. Right? And for each of these, if we had some epoxide, and then we were having it react with each of these, we would have to say, first, this nucleophilic reagent. Second, what would we add? Aqueous workup, H3O plus. So long as we wanted to make an alcohol, there may be times that you want to take advantage of the alkoxide here. You may want to take advantage of this alkoxide that forms. Maybe you want to do a Williamson ether synthesis, and you don't show the aqueous workup. If that were the case, then I would explicitly say no aqueous workup. There are some professors that actually don't care to show aqueous workups every time. In their exam questions, they'll say, assume any necessary aqueous workups. We do a lot of assuming already, and I want you guys to realize the necessity of the aqueous workup. Because if I sent you up to lab and I gave you that acyl addition experiment forming triphenylmethanol with the Grignard, and I said, go do the reaction and do any assumed aqueous workups. Where does the assumed aqueous workup show up? So I'm highlighting it in class all the time to make sure that you realize it is very relevant when you're actually doing the chemistry. Okay, then the product that we would get up here, vicinal cyanohydrin. Down here, a diol, or a vicinal ether alcohol. Down here, I'd have a new carbon-carbon bond adjacent to an alcohol. For instance, a new methyl group, or an aromatic ring. By the way, that epoxide, that 2-carbon epoxide, is called ethylene oxide. Ethylene is our carbon-carbon double bond, CH2CH2 double bonded. Ethylene oxide is just that CH2CH2 bridged by the oxygen. I didn't have to worry about the regioselectivity here. Is that right? But if I added anything to either of these carbons, if I were to add an R group, it would consistently show up where the alcohol shows up then. Because in nucleophilic conditions, I'm always attacking at the least substituted. Did that flipping around intentionally, by the way. I put the R on the left side on the epoxide and the R on the right side with each of the products, because I want you to recognize that structures don't always show up consistently from starting material to product. Sometimes they flip around in weird ways. In fact, I thought about this last year. I was at the American Chemical Society National Conference looking at posters that undergraduate researchers were showing. And I felt like they could have used some advice from a science communicator to make their structures as clearly interpreted as possible by keeping the format as clear as possible. This doesn't feel like the most confusing example, but it certainly isn't the clearest it could be. If I'm going to show the R group on the right, then why don't I just show the R group on the right? And some people just don't see that. They just draw their structure however they want. Okay, acidic conditions, the reagents that we'll use. H2O and H3O plus. Alcohol and H plus, and HCN. Actually, we'll typically show this as KCN and HCN. So in that last example, I do want to point out the cyanide is still a negatively charged nucleophile. This is still Cn minus. But it's now in the presence of its conjugate acid, HCN. So we're in acidic conditions, and this will protonate the epoxide before anything attacks. Well, when water opens the epoxide in acidic conditions, I still get a vicinal diol. When my alcohol opens the epoxide and when my nitrile opens the epoxide, nothing really clearly changes until we start trying to reference a more substituted carbon from a less substituted carbon. And now in this case, it's the nucleophile that adds to that more substituted carbon. Okay, that's essentially it. Those are all the reactions. Now we just need to plug and play. But I do want to point out something interesting about epoxides, a chemical pattern that shows up when we start using epoxides in synthesis. You'll notice a lot of alcohols. It's a lot of alcohols being formed when an epoxide ring opening is happening. Epoxides often lead to they'll often lead to a new alcohol being formed and a new group being added to the structure, and those two things are often 1,2 related to each other. Here I got an alcohol and an ether, and they're 1,2. Here I got an alcohol and a new carbon-carbon bond, 1,2 to each other. So it's this 1,2 pattern of an alcohol forming and a new group being attached that can suggest that an epoxide would be useful in that synthesis. Okay. What I would like for you guys to do not all of these involve epoxides. I would like for you guys to start working on these multi-step synthesis problems. Feel free to collaborate with your classmates. Lean into each other's strengths. Try to make it make sense. I'm going to put a couple extra up on the board that maybe involve epoxides a little bit more. I think there are very few on here that actually involve epoxides. Then I think maybe around 6, I'll tell you guys to take a break anyways. And around 6:15, we can start working on the homework problems. So I want you to get some practice with these. And then I want to see if you can finish your homework before you leave tonight. Okay? I'm here to answer questions.
Are you guys joining our table? NaH? Why wouldn't it be NaH? Okay.
So we put HCN on it and then like PBR3.
Couldn't you do it without an epoxide though? Sure, go for it. The orange.
I was wrong. There's at least 2 epoxides on this sheet. 2 useful instances of epoxides. It doesn't just take, the NaH doesn't take the bromine. The NaH takes the hydrogen from the alcohol. And that means I have a good nucleophile. But this, you'll never isolate. This reacts with itself before you could take it out of the reaction and analyze it. So it looks like you just go from halohydrin to epoxide, but there's this intermediate.
Okay, thank you.
Mm-hmm.
Can you just do SN2 for this whole thing?
No.
Why?
In fact, I don't know if there's a single SN2.
Why couldn't you do SN2 for this bromine right here? Because there's a faster way?
Okay, so tell me what you'd want to do.
Because if I put
And-
an OH, it will
Okay.
substitute this bromine
And it will change that stereochemistry.
so that it's flipped, so then that's a...
And then how do you get rid of the other alcohol to be a cyanide?
That's what I'm trying to figure out.
Especially without doing the other alcohol that you just put on.
Well, can you make it into like an OH2 and then react it with HCN?
Okay, so you're thinking like, and in acidic conditions, substitute the alcohol with CN, which is kind of valid, but not a reaction we actually learned.
You said it would work, but that's not what I'm looking for.
I mean, it's something I've never seen, so we'd have to go test it.
We could go test it.
But what about this? Your final product, does it have an alcohol?
Yes.
And does it have a new group vicinal to the alcohol?
Yes.
What's vicinal, Peyton?
Next to.
Good. 1, 2. Why didn't I put vicinal on the board? Why did I say 1, 2? And then could you get a cyanide on there if you had an epoxide starting material?
Yeah.
Yeah, actually, you can control whether the cyanide goes more substituted or less substituted as well.
So I missed the part where we were making epoxides.
You've got to, you walked in late.
Yeah.
Actually, we learned that a halohydrin starting material can be used to make an epoxide.
How?
My brain doesn't work in multi-step synthesis.
Is that why you show all your intermediates? I was thinking of yours predominantly. You did a great job,
So
And like I will.
but
I
it
will
must
do
have
it
taken you a
faster.
lot of time.
Yeah, but it's like for me to actually think through it. Like I think that like last problem, it took me like 45 minutes because, and it wasn't because I drew it all out. It's just because my brain doesn't work for multi-step synthesis.
Let me ask you another question. Do you take bio classes? Are you a bio fan?
aren't you a biology major?
I am a biology major, and I wish I was a chemistry major, but I'm not. I don't want to go all through calculus.
But you haven't done biochem.
Not yet, no.
I'm trying to think of something that, because I don't know a lot of biology.
Krebs, the Krebs cycle.
Do you know the Krebs cycle yet?
Not in detail, no.
Okay, because in there, you're just seeing major changes in functional groups without seeing how the bonds are forming and breaking.
You don't have to do.
And similarly with sugars like glycolysis and neoglycogenesis.
Close.
What is it?
Gluconeogenesis.
Thanks. I thought something felt wrong about it.
good
You
enough.
you look at all these major changes in functional group
Yeah.
without looking at how bonds are changing step by step,
You don't have to.
which is very similar here. Look at how the major functional group changes
Okay.
without needing to prove that underlying change.
Look at like how they change.
Yeah.
So Casey.
And think about what you can do with them. Here's a halohydrin. What can you do with it? Can form an epoxide.
I love that my brain is here processing like halohydration.
Halo,
Yeah.
hydrin.
That works with epoxide.
Back in OChem 1, we learned about the halohydrin alkene addition.
Yeah, which
At the start of OChem 2, we reviewed it.
I'm just gonna
At the start of this alcohols chapter, we reviewed it
Can you write
again.
this down? Can we run this back?
well, I remember that because isn't it like, is it BR2 and H2?
Yes.
That it is? 'Cause
Yep.
then it becomes HBr, right?
Yes, you get a byproduct of HBr. Good.
So is this
I
right?
kind of remember.
Off to a good start. This
Yeah, it's probably
this won't react. There is something we can do to that benzylic position, but it's not with water and acid.
well, it will get us an alcohol group up there, right?
No, not in one step.
Next up. Wait, would we do like a substitution and then do another substitution to put alcohol on there?
If you wanted to, although I'm not sure why you'd want an alcohol on there.
Okay.
You're seeing the alcohol in the final product, and you're trying to get it on there now. Is
Okay,
that
I see what's going on. Okay, you want us to make a carbonyl and then you turn it to an
maybe? But let's think about one of my rules of multi-step synthesis is map your carbons. How do your carbons change through this process?
Like I said, we gain kind of like this, what would you call it, like an ethylene group?
Great.
Ethylene group and then an OH group. Right.
So if I call the benzene ring 1, 1, 2, 3 becomes 1, 2, 3, 4, 5. So I don't want to do anything at 2. You mentioned add an acyl group. I assumed you were thinking about acyl addition,
Maybe.
but I don't want to form a new carbon bond at 2.
You want to form it at 3.
I want to form it at 3. And I want that new carbon group to be vicinal to an alcohol. Do you see that?
MgBr and then Br.
I get this ethylene group attached to a carbon vicinal to an alcohol.
So it's at the 2 position, right? 1, 2, right? Is that what you mean?
Yeah, like
So if alcohol is
alcohol here, new carbon group here. So it's like 1, 2, I form an alcohol, I form a new group. Yeah?
yeah.
I know it's hard to see sometimes.
Right, yeah.
Maybe instead of starting our benzene at carbon 1, we call this 1, 2, 1, 2, alcohol at 1, carbon-carbon bond at 2.
Beyond the 2 position.
So then, it seems like I could use an epoxide. And if my epoxide is 1, 2, I'm attacking the less substituted of them, forming a carbon-carbon bond. The only one that would do that is...
Okay, right, because that disposition right here, B3 or 2, that's the least substitute.
Yeah.
Therefore. Oh, okay.
Now remember, my other rule, map your carbons, brainstorm. Brainstorming is what we just did with that 1, 2 thing. Maybe I can use an epoxide. Now work forward and backwards. Seems like we might have an epoxide. You could figure out what that looks like, and then keep working backwards to figure out how to go from here to an epoxide to get to here.
Okay.
Okay.
Yeah.
And flip through your notes. You've got a benzylic carbon. What can you do at a benzylic position? How are you doing? It's a lot, huh?
Yeah.
Do you want to work with somebody?
No, I think I just need to struggle through it. I just have not been studying.
There's still a struggle in a partnership.
Yeah.
It can be a more productive struggle because you can bounce ideas off each other. Or if you want to talk with me,
Yeah.
I'll hear you out on some of your thoughts.
Well, for this one, I was thinking the NaH, because that would create the oxidation.
Yeah. Yes, that's exactly what it would look like too.
And then it would do this. This CN.
But here, what you've given me, I think you've tried to combine acidic and basic conditions.
Okay.
It looks like you're giving me basic, but following it up with acid. Oh, no, sorry, that's actually exactly our nucleophilic conditions. But according to that,
Yeah.
the nitrile should attack at the least substituted of the carbons. And it's not going to add to the more substituted. So instead of nucleophilic 1, 2, I could run this as acidic, HCN. HCN is acidic conditions,
Yeah.
which will allow my nucleophile to attack at the more substituted position. So this process,
Doesn't exist.
this wouldn't form from this.
Okay.
This would form, well, and actually you're right, this doesn't exist. It actually, can I show you? It's actually, well, it's like this. The nucleophile opens.
What'd you guys vote for 2?
For 2? Well, we're trying to look for reaction still.
For the first one?
Oh, for the first one?
No, we finished the first one. Wait, I do want to know what you did for the first I don't think we finished the first one. I'm like 90%.
All in one step. So there's no carbocation for it to attack. Because if there was a carbocation, then the cyanide could actually attack from either side.
No,
And I wouldn't get a preserved stereochemistry. It's only if the cyanide causes the substitution that I get that inversion of stereochemistry.
Oh, that's what we're talking about, right?
I don't know what you're talking about.
She's talking about
Is this
they're talking
valid?
about the
Or are we still
stereochemistry
making
version.
epoxides? Sorry.
No, go
I
ahead.
didn't mean to touch you.
You know what? I actually,
Oh no.
I have been, that has been going across my mind since Tuesday because I tried to get your attention the other night and I poked your back and then I said, "Good job, Peyton." And I was like, I could have just used my words.
And then I'm like, I didn't mean to.
Did not need to poke her like that. I'm not
That's
Joe
okay.
Biden, you know.
It's okay.
I wanna ask
Listen,
about the first
listen.
one.
What's been running through my mind on a loop is
Well,
the
no, so they
Amazon
did the
thing with the
KCM and
beanie.
the
I was like, I was so
HCM.
mad when I left that day. I went home and told my
Oh.
boyfriend about it. I said, literally everything in
did
my
the
wardrobe is
CNHD.
thrifted. I was like, and the
Oh.
one thing this man asked me about is the one thing that I bought off Amazon. I was fuming.
Bummer.
I was like, he doesn't
Oh. Oh wait, does acidic give you more substitute?
This is creative, but it is not valid.
Trying to rival.
This one especially.
Oh wait, could you do
Nucleophilic is
MGBR?
less substituted.
Not off of an O. No. The carbon will bond to MGBR, but oxygen will not.
So what if you just put MGBR and then a second reaction with this?
Now, this reagent I don't think can exist. I've never seen anything like it. It looks like a really good oxidizer.
Wait, can I ask you what was I
I'm just making stuff up right now.
Yeah, I can see that.
It's because
But I would encourage you to lean back on things we've already done. What is this functional group? Sorry, Camille.
Ester.
Have I shown you a way to make an ester?
Is that right?
But I had it a second ago, and then I was like, yeah, we'll do that.
No. I don't know.
Where is it in your notes, Peyton?
I don't know.
I think Camille is feeling pretty confident,
Well,
and she's starting to second guess why she's listening to you guys.
well, she should absolutely.
I don't know what's
I
going
just didn't understand.
That's okay.
I was in my own.
So remember, one of our rules with multi-step synthesis is work forwards and backwards. If you're not sure how to work forward, try to go backwards. So you've got an ester. How have I shown you how to make an ester? I'll tell you this. I've only given you one way.
I literally don't know. Is it?
Oh, I know
Did
what
we
it
do
is.
it today?
No.
Yesterday? When?
Yeah, it was Tuesday.
It's the
These ones?
acid catalyst alcoholysis, right?
Well, acid catalyzed
Oh, wait, no, that was
alcoholysis
ether.
forms an
You
ether.
said ester.
Because remember, I also called that
halo
one.
Ether?
Esterification?
No, because that also forms an ether.
What am I doing?
You're looking for an ester.
I don't know what I'm doing. I'm sorry.
It's right there though. It's right in front of you.
That one?
Yes. You don't have a name for it, huh?
No, what is it?
Acid catalyzed esterification.
That's what I said.
I trusted you.
I said esterification.
Esterification.
Wait, esterification.
Yeah. I could see it in your eyes that you knew what it was. I needed these two to get there.
Oh, I was like, when you said no, I was like, that's me.
No.
Oh yeah, because an ester is a carbonyl and then the oxygen, right? That's what
OR. Carbonyl OR.
Oh, and then we can
carbonyl.
Wait.
OR.
I'm still.
Because the acid is carbonyl OH.
Yeah.
Ester is carbonyl OR.
So you need to put an oxygen on
So we
there?
can take, can we take one of the, where is it? Where is
then
this? One of the double bonds
Ether,
and then make
Oh.
an alcohol from it with one of these, and then we go back and make the alcohol into the ester with the ester.
You're definitely going to want to make an alcohol,
Yeah,
but you can't do an alkene addition on an aromatic ring.
So can
because
we?
then make it, we can't like make it on an aromatic and then make it aromatic again.
No. Well, I mean, in a way you will, yes. The reaction that puts the alcohol onto the ring will break aromaticity in a reactive intermediate, and then it will reform aromaticity.
We don't care about.
Okay, wait. So
And we've learned a reaction that does that.
Yes, okay.
And it should have been on this sheet, but it wasn't like, or sorry, it should be associated with that sheet, but it wasn't in that flow chart.
Oh my gosh, wait, I know how to do this.
can we?
It's
still do.
Does this say Aryl Edition?
I changed it down here, but I must have.
Okay, because that's what Jackie had too.
Dude, I think it has.
I really,
I think you did because I had to change my notes too.
I was gaslighting you all.
Yeah.
Sorry.
No, I wasn't gaslit. I just.
Apparently, I wrote Aryl Edition. I bet it was just a bad C.
I think so.
I wrote Acel Edition, but I think it looked like Aryl Edition. Because my C's do look like R's sometimes, and my C's look like U's.
Add BR and then add OH?
We have to put.
Or can we just add an alcohol?
You can't add an alcohol directly.
Okay, so can I add a BR and
Yes.
then add an OH?
Yes.
Okay.
But heat is not the reagent you need with BR2.
Huh?
You'll need a catalyst.
Well, that's why I said you're number 2, right? Because I was like, oh, well, you have to put an alcohol on it, but then
So if you need to, review your reactions with aromatic rings.
put a halide on it, and then you can swap it for an alcohol, right? And then you can do the ester.
Yes, esterphophysiphus.
So how does this reverse the stereochemistry?
Well, I think you, again, are assuming that it opens into a carbocation. But the cyanide attacks here.
So does it at the same time?
This never exists.
Okay.
So, yep.
And it happens at the same time. So.
That's why the stereochemistry inverts.
Okay.
Imagine 2 people sitting in the back of a cab. And the guy on the right is going to get out, and another guy is going to come in from the left at the same time. So what happens to the guy that stays in the cab? He has to get pushed over. So think of that as chirality shifting. The group that's leaving comes out, a new group comes in, which pushes the other group up. I saw, actually, that was an Instagram video I saw, and it was like SN2 reactions be like. How are you doing?
I have a quick question. Okay, so for the first step, we're not doing anything that will manipulate that carbon over here, right?
I would,
You would? So like, something like this?
but this will take the entire carbon chain and cleave it off and give you carboxylic acid.
Okay.
And to be honest, you could get to the final answer that way. It's not the route that I had intended, but there is a plausible route that goes that direction. So if you want to pursue it, you just have to know that it doesn't make a ketone. This will make a carboxylic acid. And our mapping that we did, you just cleaved off one of the carbons, so now you're going to have to consider adding a new one. What other reactions have we seen that allow us to place something at the benzylic carbon?
Let's say going back to like EAS or something.
It's actually going back before EAS.
So NAS?
Before NAS. Because EAS and NAS place things on the aromatic carbons. And that was section 16. In section 15,
Yeah, like an anti-Markovnikov type of situation.
not really, because I don't have an alkene. So I can't manipulate an alkene. I have to manipulate just the benzylic carbon.
Carbon.
And back in section 15, we did look at that. This was a reaction from section 15. Oxidation of benzylic carbons.
Oh, okay.
So in that section, you'll find a reaction.
Right. Okay, yeah, the only thing I remember from that is like wolfification of clevis.
Yeah. And this, apparently. But there was one other reaction.
Right, so it's like almost like the opposite of like a Lenz's.
Kind of, yes.
Yeah.
But it's not going to give you a ketone.
Right, okay.
That's not the right thing.
You've made some progress, huh?
A little bit, but I'm a little lost on the this one. It's probably the easiest or something, but
Well, you're on the right track.
yeah.
And I would say you're one step away.
Yes, I'm just wondering because this is definitely a kind of like a dehydration reaction.
Mm-hmm.
But is this gonna be where it happens?
Why not?
No.
You're thinking that it would instead dehydrate to the right?
I mean, this one will be more stable, but
Why?
because it's more substituted,
That's true.
and it's also next to the carbon.
Conjugated.
Yes.
So more substituted and conjugated, double whammy.
Yeah.
Otherwise, we could have a situation where we have to consider more substituted or conjugated. And those both have their own stabilities. So we'd have to weigh, how do we predict which one will happen? Maybe both will.
Okay. And then this one here, I feel like it's too long. I basically went a long.
Oh, wow. Yes, you did. But it doesn't, it's not wrong. It works. There is a way that you can do it in fewer steps.
Okay.
Actually, no, it's not fewer steps. It's just different steps.
Okay. Okay.
So I'll encourage you to try again.
Yeah.
And after you get to this point,
Yeah.
try to use an epoxide.
Okay.
Okay?
Yeah.
This one looks great. This one looks great. The only thing here is I want you to show NaBH4 first,
Yeah.
H3O plus second.
Okay.
So 1, 2, which here, you don't need to show these as separate steps.
Okay.
You can show it as 1, 2, and then skip the alkoxide intermediate.
Okay.
Same thing for this one.
Yeah. All
Deal?
right. Yep.
Okay.
Okay. Thank you.
So really the only one left is this one, trying to use an epoxide.
Okay.
And then if you're feeling up for it, Milena, you could join other people and try to help them reason their way through some of the reactions. If you're feeling up for it.
I need to know
I need to
chemistry
know.
behind this.
We're going to cover it in Unit 4.
But like right now.
You need to know the mechanism.
Well, I mean, yes.
Okay, well, acidic conditions.
Wait, what?
So my carbonyl gets protonated. Acidic conditions.
Yeah.
You agree? Because we said H+.
Yes.
Okay, so this guy gets protonated.
Because it's a carboxylic acid and H plus, right?
Yep.
Okay.
And the carboxylic acid, carbonyl oxygen, gets protonated.
Okay.
Acyl addition. We call this a tetrahedral intermediate.
Okay.
Oxygen has done acyl addition. And then that oxygen
Oh, it took one bond back. Okay, then there's. Because does that mean there's
gets deprotonated before this other group gets reprotonated. Sorry, I'm skipping some steps.
No, it's okay. Because so at one point there's technically 3 alcohols on there.
I wouldn't call this an alcohol, but I do see what you mean. I would actually call this, I would call this a protonated ether. Because it's ROR, but it's protonated. But you're right, yeah, there are
So then
3 OHs at one time.
There is an elimination.
This guy gets deprotonated, and then this guy gets protonated. I'm showing that happening at once,
yeah.
but actually in Unit 4, I'm going to have you show each protonation and deprotonation step. No skipping. Textbooks will often skip, but guess what? I'm not a textbook.
So then is it the oxygen that's protonated, right? In the second step?
Here.
Where does it get rid of its hydrogen then?
No, it takes the electrons away from carbon, and it leaves as water. OH2 plus leaves as water. This, oh, you're right, yes. This oxygen on top, it does have another hydrogen.
Well, I was talking about the hydrogen that's attached to the. Oh, but that only works with the. No, that's this one. Oh no. Yeah.
Yeah, this one loses. This one gets deprotonated.
Yeah, so it gets rid of its hydrogen
Yep, yep.
So then it doesn't have a positive charge, it's just this.
And you'll notice that becomes the ester
Yeah.
oxygen.
And then
One of these two picks up that extra hydrogen.
oh, and so that one picks up the extra one, and that one leaves. Okay, yeah, okay.
Good,
Thank you.
good.
I'm gonna take a picture of that.
Sure, it's the messiest thing I could have given to you.
No, it's okay.
And it's all in one color, so it's hard to read.
Oh, I don't care. I just so confused.
I would not do nucleophilic conditions
That's okay.
for this epoxide opening,
That's okay.
because that means the nitrile should attack at the least substituted carbon, which would be the secondary.
I can probably tell you the mechanism, but only after I see the product.
If we want it to add to the more substituted position, we'll need to show it as acidic conditions.
Oh, so more substitute is acidic?
We'll use acidic conditions to add it to the more substituted.
Oh, okay.
Yep.
I know it's like long, but there's but right, that's gonna make a carboxylic acid, and then somehow you want to take out this alcohol, right, and then somehow add on to the ethylene group.
Okay. So, one thing, not an alcohol.
Oh, well, not yet. It's a carboxylic acid.
It's a carboxylic
It's
acid.
a hydroxide group.
It's actually not a hydroxyl group, because a hydroxyl is what we call the substituent of the alcohol, and it's not an alcohol. I call it a carboxyl group. It's like hydroxyl. It's an OH. But being bonded to the carbonyl completely changes its chemistry.
Okay.
For example, this OH, an alcohol, sp3 hybridized. But this OH, a carboxylic acid, is sp2 hybridized. It has a lone pair in a p orbital that's constantly in resonance with the other oxygen. Now, your idea to substitute it, it's not a bad idea. HBr won't do it, though. We actually could do it with PBr3,
Yeah.
like we do with the alcohol, but then it looks like you're proposing EAS, but this is not an aromatic ring, so EAS is not going to work.
Okay.
So, not a bad idea, but it's not quite going to get us there.
Okay, so
The last thing to point out is your reduction step should be first NABH4 and then second H3O+.
okay, that.
Just the aqueous workup.
Okay.
So this step works, but it's these steps in the middle that don't work.
Wait, so which one works? Sorry.
Step 1 does work. That gives you what you expected, just like the chromic acid would have.
Okay, but that's.
And this reduction step works, but it's this transition and substitution that doesn't work in the middle.
But could I add a halide, like in place of the OH or no? That's just not.
You're not going to need it. No.
No.
You can do it, but you don't need it.
So then should I have made like a ketone instead of a carboxylic acid?
No.
No.
In fact, I would try to aim for making an epoxide there. But if anything, you'd want an aldehyde.
An aldehyde. Okay. And then is the idea to then take that, like, and then like add the ethylene onto that aldehyde, or like.
No, the idea for me is add the ethylene onto the epoxide. Because remember, if you get down to an aldehyde, you're losing carbon 3.
Yeah.
So instead of just adding 4 and 5, if you lose carbon 3, you're going to have to add carbon 3 again.
Right. You have to add more carbon.
Yeah.
Okay.
There's
So
more than one right way.
basically none of this.
That's how I feel too. I was like, and none of them
Yeah.
are in the same place. And like
The first step, the oxidation, definitely. And if you want to get to an aldehyde, you're going to need a couple of extra steps to go from carboxylic acid to aldehyde. So see if you can do that. See if you can take that benzoic acid you just made and create benzaldehyde. How are you doing? You move down to this one? Anything stand out to you that you're brainstorming?
Magnesium.
Okay.
Because I know you can combine, like form a ring. So can you?
But correct me if I'm wrong. This is breaking a ring.
Yeah.
So I'm not sure that carbon-carbon bond formation is what we want. We actually want carbon-carbon cleavage. Can you name this functional group?
The ring?
The two alcohols adjacent to each other. Oh, I screwed up on the structure. You mapped your carbons correctly, and I'm short a carbon. I'm going to point that out. Hey guys, how many typos do you think we'll point out before the end of the night?
Oh, did we already find
Yeah, on the bottom right structure, I started with a 6-membered ring, and I ended with a 5-membered chain.
Woohoo! You got rid of a carbon!
Okay, that helps.
So it should have been a 6-carbon chain.
Yeah, that's way better.
Way easier. Thanks, Yvonne.
You guys are already down there?
We scared.
Oh.
So I think if you can find that functional group and a way to react with it, you'll find a way through to this synthesis. James Milena followed a very similar process to you on that first problem. If you want to chat with her and pick her brain about it.
We're crashing out over this one a little bit.
That is what I would do in the first step, but it's not what I would do in the second step.
Don't turn it into an OH.
The alcohol is not going to bring any benefit. No.
Okay. We are really stuck with how we're getting this whole side chain on.
Yeah. Yeah, side chain. Carbon-carbon bond formation, right?
Yes.
Yeah. It can be, but it doesn't need to be. Let me tell you, this synthesis has a lot of correct answers. A lot. I have a preferred synthesis, but can I actually step back and talk to you guys about the top right synthesis?
Don't look at mine, you can't read it.
I already did. Which is to say I already did read it.
It looks,
Yeah, and your ring lost aromaticity. Water is not a strong enough nucleophile.
Can you do NaOH?
You have to do NaOH.
That's the thing. Okay. I couldn't find that in my notes, but it's in my head.
It's literally right there.
Oh. Well, that's lucky that I turned to that page right then.
Yes.
Bill.
And what is that reaction, by the way?
The NaOH?
Yeah, substituting an aromatic halide. NAS. Which we learned about before EAS. There you go. Right there.
Wait, what to protonate? Do an SN2 reaction to get rid of
He keeps talking about how iodine is a good leaving group, so there's that. Oh man. He just keeps talking and talking and talking. If you wrote that every time I just kept talking, your whole thing would just be.
whenever you point something out, I'm like, maybe that's gonna be on the test. I have to write it down. I probably did too.
So funny.
Yeah, I try to.
So many things like that always bug me, and I've never heard a professor talk about it.
Bugs me too. I've thought about writing a proposal to IUPAC and asking them to remove the name of dead people and living people, remove the name of people from named reactions. Let's name them for what they do. Like you brought up some coupling reactions, which are all named after people. The only one that I can ever remember is the Suzuki coupling, but I can't tell you what specific combination of groups is needed. If I reviewed it, I could tell you, but we could call it like the the aryl boron coupling reaction, and at least then you'd know boron's involved. Anyways, so bromination of the ring, great. Substitution with NaOH, good. Water is not strong enough to do it. Then it looks like you wanted to make an ester,
Yes.
but you added a peroxy acid. Any reason why? A peroxy acid, by the way, is the carbonyl to OOH. Peroxy. It's got an extra oxygen. This is actually not a peroxy group, but it looked like this was. Well, I guess that is hard to read.
I tried to rewrite it down here for myself.
So I guess I'll ask this. Why is it that Andy has a different functional group than you guys?
That's a good question, Andy.
Sorry. Sorry, everybody.
I knew that we needed to deprotonate
And
create an
Indigo, I'm not sure what your functional group is.
an ester right here.
Don't look at that.
And by ester, I meant ether.
No,
Little ester,
Ester.
and we need this little
es-
connection right
ester
here.
linkage. It's not an ether.
What is this?
Ignore it.
Yeah, that's why I wrote it down
Oh,
Yeah, don't look at my notes.
So if you have an alcohol,
okay.
and where were you referencing? You had notes somewhere, right? Yeah, if you have an alcohol and a carboxylic acid, you can make an ester. What you've drawn is a peroxy acid.
Wait, so this thing is what I need?
That's right. Well, not with that carbon chain though.
Okay.
You need the carboxylic acid, CO double bond OH, and whatever carbon chain you need. It's not up to me what your carbon chain is, it's up to the structure.
This is the agent, right?
Yes. Yes, but not with that carbon chain. Yes. Great.
I added a carbon. I'm known for that.
You didn't add a carbon, you added an OH.
I add lime. They just.
You added an O.
Like right here.
The group that you had is a real group. That's peroxyacetic acid. That does exist. That would be useful. We abbreviate this, by the way, as CO3H. Useful for making epoxides. We're going to see it again in Unit 4 for making esters from ketones. So not useful in making an ester from an alcohol. So it was real. And because of that, it's quite different.
Are you gonna go over these on the board?
Oh, maybe we should, but I never even told you guys. You want to take a break? Doesn't seem like it. You lost a carbon here.
I do all the time.
Yeah.
They happen.
Well, this is why one of my tips in multi-step synthesis is map your carbons. Makes it harder to lose them. Okay, but now your alcohol's on the wrong carbon.
Dang it.
So map your carbon. I'm going to leave you so you don't feel this pressure.
Can you help with this one actually?
Sure.
Because I'm still lost.
So my recommendation, look at that final product and notice how you add a new carbon-carbon bond, vicinal, to a new alcohol, to an alcohol. You've got benzylic, and you've got the carbon next to benzylic. 1, 2. Benzylic gets alcohol, carbon 2 gets a new group. So try to see if you can make an epoxide. And what type of group would you need to add? Nitrile? Alkoxide? Grignard? If you're going to form a carbon-carbon bond, you have to have an organometallic to make that carbon-carbon bond. Can I ask you guys to add your negative charge to hydroxide?
Oh, yes. Because that would be a nucleophile, right?
Well, yes, but also it would be misrepresenting hydroxide.
Okay, on this one, did I write this down? You said I needed to change this, but I wrote down that
Yeah.
I wanted to add our alcohol, less substituted.
Okay,
I wrote that acidic OH less substituted.
that's right.
So,
But this is not acidic. This is basic followed by acid workup. 1, 2. The only thing you've done is you've added K. You've added K as a counter ion. No 1, 2.
Oh, so it's not 1, 2 for the acidic.
It's not 1, 2.
So if you give it 1, 2, it's fine.
If you give me 1, 2, that's not the structural isomer you make. You erase the 1, 2,
Oh, okay.
now you have acidic conditions.
Can I have you check the reaction in a second?
Yes.
oh, so that's an or on there. HCN is an or.
No, it's like saying methanol and acid. I've got my nucleophile, but I also have acid.
Right.
This is essentially the same as this. That's true. But now it's in the presence of acid. HCN is its conjugate acid. So we're in acidic conditions now.
Right. Is H3O also an acid?
Huh?
Is H3O plus also an acid?
Yes, but that is an acid workup. I do it after everything has finished with my nucleophile.
Oh, okay.
I think you are right, Elliot, that it probably would have been just as fine for me to just label it as HCN.
I was just getting confused. So in acidic conditions, yeah, you don't need the acid workup because it's already.
Already acidic.
Okay. Yeah, that makes sense. All right.
So yeah, get rid of the 1, 2, and you've got it. And then you're close on this structure, but you've missed a very important element. You've got it, Max. Can you spot the difference? He's got his acid. He's got his OH.
Yeah. This is not, that's just a carbon, so I guess. Oh, or am I missing a carbon?
Oh, are
Nope.
you talking about the fourth
It's
one?
bromine.
That's why I started and I'm oh, this is unactive.
You
It's like, I recognize it.
have an enol, not a carboxylic acid.
Oh,
Is that what it is?
yeah, okay.
Yep. Isn't it crazy how one little circle is...
You're walking over as I was writing it. So.
I know, I noticed that. I was waiting for you to finish it
That
though.
one, right?
Great. I do want to see 1, 2 with the reduction. First the reducing agent, then the acid workup.
Oh, yeah.
Because if you have NaBH4 in H3O+, it destroys itself. Do you guys want to start working on your homework? And I'll start putting... Johnny said to wait? Oh, okay. Okay. Yeah, feel free to take a break. Do you want me to start putting answers on the board?
Yes.
Okay.
This might know either organometallic or organometallic.
Yeah, just give me the lab procedure. I'll tell you how you do it.
Acid.
Boy, I couldn't tell you what any of them were anymore. Okay, as I put these up there, I would encourage you to maybe start looking at the homework, get it ready so you can spend the next 20 minutes on it. Do you have a name for that? The O to tert butyl? Yes, tert butoxide. I heard Elliot say, just look at the lab procedures, you'll know how to solve that one. Which is true, but I did change the chemicals for that reason. Oh, hurts my arm. Oh my goodness. Because I'm not like lecturing and wandering back and forth to my laptop, I haven't been checking it, and my phone is at less than 5%. And that video is gonna cut out. Saved it. Ooh. Because I really just hate when it fails the recording. Yes, I heard that. Trust your instincts.
John, on the first one, you have the OH on a dash on the paper. Or not on the dash.
Oh.
Wedge.
And that is correct. Thank you. Because when the epoxide breaks open, it preserves that wedge. Thank you. Did you guys catch that? I drew that as a dash. But you might not have even been copying it down. I think I told you guys, but in the fall, we did not go through this worksheet. I ran out of time to even put that information about epoxides up on the board. So we did something right this semester. I just need to figure out what. It might have been not talking about the unit test. I didn't talk to you guys at all about it, and that's because I was a week late on grading. My apologies.
That's way better than a lot of professors.
Yeah, that's, don't hold me to their standard though. There are some alternative paths for some of these.
Active likes using the alternative paths.
I mean, I get what you mean, but there's a reason that I have you guys do written work, and it's because there are assignments that there are exercises I don't trust with active. Multi-step synthesis being one of them, where you have to guess everything in the middle. I don't trust leaving that with active. and, mechanisms. I need you to put pen to paper for mechanisms to practice it before the exams. So I can't have you just point and click on active. One alternative mechanism or synthesis is here, where styrene, vinyl benzene, is cleaved by reductive ozonolysis, and then we simply add on a carbon to our organometallic, and we get the same end product. But there's an additional, completely different synthesis route. If I take ethyl benzene, and I think I'm realizing that in this, I didn't use a lot of strong oxidizing agents. I never had you distinguish between chromic acid and PCC when oxidizing a primary alcohol. So this is something I'm always trying to improve in my worksheets, is the diversity of the reactions I use. If I took my ethyl benzene and I oxidized it, I could take it right to benzoic acid, which is not useful for doing acyl addition because the benzoic acid is an acid. So if I introduced an organometallic, it would just deprotonate and ruin my organometallic. So I'd have to reduce this down to benzyl alcohol. And then I could mildly oxidize it to benzaldehyde, which then goes through the same acyl addition step. I think as a student, sometimes it's nice to see that there are multiple ways that you could solve a synthesis, because it means that if you feel like you're onto something, you really might be. And other times it's nice to know that there's just one route and you just have to figure it out. But I always say that multi-step synthesis is by far the most challenging part of organic chemistry. I believe that you could memorize all those reagents and what they do, but it's figuring out how to apply them in a sequence where you're not even given the intermediates. You have to figure out how and when to use them. It is that fine line between critical thinking and creative thinking. Or another way of looking at it, multi-step synthesis is an example of how critical thinking requires creative thinking. They're one and the same. You have to be able to analyze what groups are present, what can be done with them. With this ethyl benzene, there's really two things you can do. Radical substitution at the benzylic position, or benzylic oxidation. Those are the only two things you could do with that compound to get somewhere close to the end. And being able to think critically about what you can do is important. But then being able to think creatively about how those two different pathways lead you to the final product is important. So those are really two sides of the same coin. Okay. Any questions on these? Feedback on these? Remember that I wanted you guys to recognize that epoxides are useful for getting this vicinal alcohol to a new group. So let's look at how that showed up here. I had an alcohol and a halide, but then in my final product, I want an alcohol, and on the adjacent carbon, I want a nitrile, a cyanide group. So those are vicinal, 1, 2, an epoxide intermediate is useful. And then on my ethyl benzene, let's call these carbons 1 and 2. In my final product, I want an alcohol on carbon 1 and a new carbon group on carbon 2. The fact that I formed a carbon-carbon bond vicinal to where I formed an alcohol is good evidence of an epoxide precursor. And I'm telling you guys in multi-step synthesis to not just try to work forward, but also work backwards. Hey, these look vicinal, so maybe I have an epoxide before it. If I have an epoxide before it, I need to have an alkene. I could get that alkene by putting a halogen at the benzylic position. Work backwards as far as you can until you see a route forward to meet it there. Ultimately, solving a multi-step synthesis requires really good access to your reactions and a roadmap of your reactions that show how the functional groups change from one to another. So I am once again encouraging you to make a table of reactions. I've had students in the past tell me that they have spent entire weekends building these table of reactions. What are your reactants? What are your reagents? And what do you get as the product? What's the functional group you start with? What's the functional group you end with? Hours just to build a table of reactions? Well, how else are you going to study? No, tell me, like, how else do you plan on studying? Because if you don't know how to spend hours studying for this class, this is a really good way to spend hours studying. And you know this is a 4-credit class? So do you know how much time you should be spending outside of this class on this class? Like 3 hours per credit, or 4, so 12 to 16 hours outside of class on class material. You can count homework towards that time, written work and active. You can count taking the practice midterm towards that time, but you can count building a table of reactions towards that as well. It's really useful. In fact, I did it when I started OCHEM too, because I realized how much I was going to need it. Were you going to ask something? Okay. Okay, any questions? The rest of the time is yours. I'm happy to answer questions you have on the homework, but I would encourage you to use these last 8 minutes looking at the homework problems and brainstorming. I'd even be happy to give you feedback on your brainstorming, whether you're brainstorming in the right direction or not. Do you want me to pull up the homework so you can see it? What? You have a question?
That's very unfortunate.
That whole pep talk is gone. Check.
Still counting down.
I just pressed resume. But you see how there's no more video?
Did you get the voice though? No.
No, it was paused. But it couldn't have been paused for long. But I don't know how to get the video back on. I might just call it. Okay, if you can hear this, but you can't see this, I'm sorry, because I have no idea where it ended off. On Canvas, I'll take a picture of the solutions in case that didn't make it, and I'll add the solutions to Canvas. Adios.